Hello and welcome to this lecture on successive cancellation list decoding of polar codes. A quick word I wanted to tell you about terminology here. So, I have been describing the successive cancellation decoding using the binary tree. So, Erdal Arikan in his original paper did not use the binary tree representation. He described it just using basic notation and the matrix and all that. So, traditionally his version of description of the successive cancellation decoding is called successive cancellation decoding. So, if you use the binary tree representation and use that language, the terminology is called simplified successive cancellation decoding. So, like I said, successive cancellation is the first decoder that was proposed by Arikan. So, you can abbreviate it as SC. Simplified successive cancellation is the one that we described with the binary tree. Okay. So, that is called SSC, and today we will see the simplified successive cancellation list decoding. Which is SSCL. Okay. So, I am simply calling it successive cancellation list decoding. The word simplified more or less just refers to the fact that you are using the binary tree and the language of tree traversal to describe successive cancellation decoding, but list is new. Okay. So, what is this list decoding? What does it do? And how it works in the context of polar codes is what we will primarily describe in this lecture. Okay. So, a brief warning for you, the idea of list decoding is very old. Okay. So, the list decoding is really old in coding. It goes back to the 40s and 50s, late 40s and early 50s. Some of the pioneers of information theory used the notion of list decoding. So, it is sort of natural that people tried list decoding in the context of polar codes when they wanted to improve performance. Okay. So, let us see how that works, and we will describe that in this. Okay. And of course, list decoding is usually not that successful in many codes. So, even in LDPC codes, it is sort of difficult to make list decoding work, but polar codes, because of their sequential nature, are sort of very amenable to list decoding, and one can do a lot of modifications to it to make it more interesting and efficient. Okay. So, we will not look at all the details, but at least we will describe how the list decoder works from a high level. Okay. Okay. So, what is the overview here? So, like we said, successive cancellation decoding works really well. It is soft input, soft output actually, but we end up ignoring the soft output. We make hard decisions, but it works quite well. It turns out when you compare it with other codes of the same length, it is not quite equal in performance. So, it needs some improvement in performance. It is not good enough. It is about maybe 1 dB or so lesser in performance. So, 1 dB or so poorer. Okay. So, this is just a rough number just to give you something to think about. So, people a few years back were looking for some ways to improve the performance. Okay. So, one interesting idea in this direction was list decoding. Okay. So, what is list decoding? So, usually when you think of a decoder, it takes the received vector and puts out one code word, right. So, that is how you think of a decoder. So, that is how the decoder is supposed to work. Okay. A list decoder will not put out just one code word as the output, it will put out a list of possible code words as output. Okay. It sort of says this received word looks close enough to multiple code words, and I am not sure if I want to decide between them. So, I will give you all the code words. Okay. So, in the communication chain, what do you do? The decoder gives you multiple code words. Okay. So, of course, you have to do something. So, usually what people do is use cyclic redundancy checks. Okay. So, it turns out CRC is another code that is used for error detection. It has very good error detection properties. It is very simple to use. It has a very efficient shift register implementation for both the encoding side and for the detection side. So, it is very simple to implement, and it has very good error detection properties. Okay. So, cyclic redundancy checks have been traditionally used in communication systems for a long time. Okay. So, in the physical layer, any message you send will always have a CRC bit padded to it. Okay. So, now what the higher layers will do is they will look at the decoded code word from the physical layer and check if the CRC is satisfied. If the CRC is not satisfied, the higher layer traditionally will sort of realize that there is an error, okay, and then it will ask for a retransmission. So, all these ARQs and other schemes at the higher layers, when I say higher, above the physical layer, so maybe at the even at the TCP sort of layer. So, whatever higher layer you can think of, so in that layer the CRCs are used, okay. So, when you do list decoding, you sort of use the CRC in physical layer. Okay, so how do you do it in the physical layer? In the physical layer itself, you check for the CRC. Okay, so you have your decoders now producing a list, maybe 4, maybe 8 code words. Okay, you check whether any of these 8 code words pass the CRC check, or not. Okay, if they pass the CRC check, then you accept that code word alone. Okay, otherwise, if none of them pass the CRC check, you are in trouble, and if more than one pass the CRC check, also you are in trouble. You have to then pick something by some choice, but usually, as it turns out in Polar codes, usually that doesn't happen. So, usually you have one among in the list as being the valid code word, and that will pass the CRC check. Okay. So, this observation was quite crucial in making Polar codes successful in practice. It of course adds complexity. You have to run multiple decoders more or less, but it gives that improvement, that critical improvement in performance, which makes it possible. So most of the decoders I expect for the 5G Polar codes to be successive cancellation list decoders. They will have a list in them, and they'll improve the performance in that. Okay, so this is a high level overview. Now let's go into details on how the list decoder works, how do you make it work, etc. Okay, so this is the picture, and it's a good picture to keep in mind. There are a few terms here. We'll come to decision metric and path metric later, but for now let's focus on the list decoding. Okay, so you have a message which is A bits. Okay, and the first step is to add CRC. Okay, so you add CRC. This L is the length of the CRC bits. Okay, so the way it will happen is you have the message, which is A bits, and to which the CRC will be added, and this will be L bits. Okay, computing the CRC is standard, and for instance, the standard document completely describes how to compute the CRC, how to run the shift register, etc., and how to add it to the message bits. So you take the A bits, add the L bits, you get K bits. Okay, so this is the actual message which is encrypted. Okay, so these K bits is the actual message for encoding. Okay, so you don't encode the raw bits that are received into the encoder. You add a CRC to it, and after that you encode. And like I mentioned, the CRC addition always happens, and this is very crucial for the next layer to work with the physical layer, and the layer above it is the link layer. The link layer will look at the CRC definitely. So that's very important. So the CRC is there, but you can also use the CRC in the physical layer. Nothing stops you from doing that as well. Okay, so you encode. Encode, let's say, is an NK code, NK Polar code maybe. Okay, and then you get a code word which is N bits. After that, you do BPSK plus AWGN, exactly like before. You get the received values here. Okay, so this is easy enough to see. You will get N received values, and you do list decode. Okay, so we'll see how to do the list decoding later on, but for now, let's say we assume we do a list decoding. Okay, and the list size is M, let's say. Okay, so the list decoder produces M code words, not just one code word, M code words. What you do here is, remember, the code word will also be N bits long. From there, you can find the M message words. Right, so from here you find the M message words, which each of which will contain a message cap and a CRC cap. Okay, so you check if this satisfies CRC. Okay, now you will get M of these. Each will be maybe a different message, different CRC. You check whether they satisfy the CRC, the parity check condition. CRC is usually a check condition. You can quickly check it using a shift register. The code word or the message word which actually passes the CRC is put out as the message estimator. Okay, so this passes CRC check. Okay, So, of course, there are these corner cases of what happens if none of the code words pass the CRC. In that case, you have to pick one, and there can be ways to pick one. I'll tell you that later on. And also it might happen that more than one passes the CRC. Even there, you have to pick between these code words. It turns out each of these candidates has a metric associated with it, which is called the path metric. So, I'll describe how these path metrics are chosen, and based on the metric you can decide. Okay. So, if there is any conflict, you resolve using path metric. I'll talk about path metric and how to deal with that later on. Okay. So, this path metric is an important notion in list decoding. It serves multiple purposes. It keeps the decoding complexity in control and also gives you an indication of how good a particular candidate code word is. Okay. So, you put out m code words, not all of them may be equally likely or something like that. You may not have the same belief on each of them. Okay. So, you can also put out a belief on each code word. So, this path metric is like a belief on each code word. Okay. So, that is how to think about it. Okay. So, how do you produce multiple code words at the decoder? In the polar successive cancellation decoder, this is actually relatively simple and straightforward. Okay. The reason is you are sequential, right. So, you start from the received word, you go and make a decision on the first bit. Okay. Maybe it is a frozen bit. If it is a frozen bit, then there is only one decision. Okay. So, it is going to be 0, there is no problem. So, slowly eventually you will hit a message bit and you have to make a decision based on its belief, 0 or 1. Okay. Now, you are committing to one direction there, you are making that decision as 0 or 1. That could be an erroneous choice. Okay. Even if it is an erroneous choice, maybe your decoder will eventually correct it, but the final code word you put out will always be in error because you made that one mistake there. Okay. So, now this can happen in any of the positions, not necessarily the first position, but this can happen. Okay. So, when you make a decision in the sequential decoder, you can make an error. If you make an error, you are not allowing yourself any sort of way to go and correct it. Okay. So, now what the list decoder does is, whenever you have to make a decision like that, you sort of keep two paths open in your decoder. Instead of only decoding the one path which is according to the belief, you make both decisions. Okay. So, you allow for a decision 0. So, the decoder proceeds in two paths after that at a decision point, either 0 or 1. Okay. And what you do also is you assign a decision metric to every decision you make. Okay. So, first of all, when you have a certain belief for the bit, okay, and you make a decision, your decision may be according to the belief or opposite from the belief. Okay. So, that is what is discussed here. So, if L of ui, so how do you make a decision? This belief is coming into the leaf node, this is a leaf node, let us say the ith leaf node, and then you put out a ui cap. How do you do that usually? If L of ui is greater than or equal to 0, you are going to say ui is 0, right. Okay. So, if you made a decision as per the belief, then you assign a decision metric of 0. Okay. Then you say there is no penalty in my decision, I got a certain belief, I made a decision exactly like I should. So, there is no penalty or there is no metric. Metric is also like a penalty, you can think of it. Okay. So, on the other hand, if L of ui is greater than or equal to 0 and you decide ui cap is 1, okay. So, this is like the other path, the divergent path sort of. Okay. So, this is against belief, and whenever you go against belief, you put a penalty. Okay. So, these are the two cases where you put a penalty or a decision metric, you add a decision metric to that decision if you went against belief. Same thing happens here. If L of ui is less than 0, this is as per belief, this is against belief. When it is as per belief, you put a decision metric of 0, you do not penalize yourself on that path, but on the path when you made a opposite decision, you penalize yourself. And what is the penalty? Penalty is the belief of the bit, absolute value. Okay. So, the critical thing to realize is, this is an important fact when you do this decision metrics. So, supposing I is frozen. So, this is what you do if I is not frozen. If I is frozen, what do? You always decide. So, you do not make two decisions when I is frozen. Okay. So, only one decision. Ui cap is equal to 0. Okay. But okay. So, even when I is frozen, you have a L of ui. Okay, remember that. Even if I is frozen, you have a L of ui. Okay, and if your decision of ui cap equal to 0 is against your belief, okay, it may happen that L of ui is actually negative. Okay, even though it's a frozen bit, the decoder might have come through some path and it might tell you that frozen bit is actually 1. Okay, it might do that, but remember the frozen bits were chosen so that the least reliable bits are frozen, so they can be in error. Okay, they can be in error with quite a high probability. So, whenever they are in error and the belief is opposite, you have to penalize even that frozen bit decision. Okay, so that keeps the whole thing correct and all that. So, you know which decoder is doing good, which decoder has already had a heavy penalty and so on. Okay, so this is very important to understand. So, the decision metric is assigned even if I is frozen. Okay, the decision is not changed, it's always ui cap is 0 for the frozen bit, but you will penalize if your L of ui is negative. Okay, so you will add the absolute value of that to this decision. Okay, so that will be a metric. Now, what is path metric? Now, decision metric is the metric on each decision. Path metric is sum of all the decisions you made on a particular path. Okay, so like I said, every point you can make multiple decisions maybe. Okay, and then on a path, if you made every decision, there's a penalty that's associated with the decision. On every path, you add all those penalties. The total penalty is the path metric. Okay, so the path metric is sort of like a belief of the path. Okay, path, remember, corresponds to candidate code word. Candidate code word. Okay, so the list decoder puts out multiple code words. A particular path is a particular candidate code word, and the path metric is crucial because it's like the belief in your code word. How confident are you that the code word is correct? If the path metric is very low, okay, so it's sort of like opposite of belief. I put belief in quotes there. If the path metric is very low, then your penalty is very low, and which means your belief is very high. Okay, it's sort of the opposite. Okay, when I say belief, keep this quotes in mind. It's the opposite of belief. So, if the path metric is low, then you're very confident about, more confident about the code word. If the path metric is higher, you're less confident about the code word. Okay, so this is how path metric can be used to resolve conflict. Okay, so when you check CRC, supposing you find none of the message candidates are actually passing CRC, then what will you do? Among the candidates, you pick the one with the lowest path metric. Okay, so that resolves conflict in the output of the list decoder when you want to put out one single output. And if multiple candidate messages satisfy the CRC check, once again you can pick the one with the lower path metric. Okay, so that's one way of resolving conflicting. Okay, so hopefully this is clear to you. This is how the list decoder generally works. So now I mentioned it in the context of the polar successive cancellation decoder. You can do this for any other code also. If you have a sequential decoder working for any code, you can always penalize like this, and you can always have a list, and you can do this. Okay, the fact that it works very well in polar coding is an important observation. I don't think there's real proof for these things, but people have observed it and they use it for improving performance. Okay, so this is how the list decoder works. You make multiple decisions on the code word bit depending on the beliefs. You might go against the belief. You put a penalty if you go against the belief, and keep track of a path metric, which gives you the confidence level on the particular path or the candidate code word. Okay, so this is how the list decoder generally works. Okay, now let's look at it in the context of let's look at it more carefully in terms of paths. Okay, so this view of the path is very important, and also a restriction on the size of the list is very important. Okay, so usually when you do list decoding, you restrict the size of the list. Okay, so you're not allowed to put more than 4 candidate code words. Let's say 4 is just an example. Okay, so I'll put an example here. You can have 8, you can have 16, you can have 10, you can have 12, you can have 7, whatever number you like. 4 is one example I put out. Okay, so this puts some restriction on how many decisions you can possibly make. Okay? Right, I kept saying for every decision you can either decide both, whether it's 0 or 1. Okay, but if you keep on doing it, the number of possible paths will quickly diverge. Okay, at the first place it will diverge into 2, right? So that's what is shown here. Okay, initially you start with a single successive cancellation decoder. Okay, so this is your initial starting point, and you have a path metric of 0. You're not making any decisions. You're starting from the root. You're going down left, down left, down left. You just have one decoder. You're not making any decisions till you reach U1. Okay, U1 is the first decision you make. Okay, remember U1 might be frozen. If it is frozen, you will not make this decision. Okay. So, I am assuming this is not frozen, assume not frozen. Okay. So, if it is frozen, you will continue to be in one path. Okay. Remember that. So, I am assuming u1, u2 and all is not frozen, I am not freezing anything. So, you will start diverging even in u1, but in case u1 is frozen, right, you will continue in only one path, but your path metric may not be 0 anymore. Okay. It may be non-zero. Okay. So, we will look at the more general situation soon enough, but for now let's continue with this simple picture to see how the thing evolves. Okay. So, you come to u1, you are assuming it is not frozen, so you make two decisions, 0 and 1. Okay. 0 will have some penalty which I am calling dm1 of 0. Okay. It gets added to the path metric. So, the whole path metric becomes dm1 of 0. So, remember this is always the path metric. Okay. The sum of all the decision metrics. One of these will be 0. Okay. So, this one of these will be 0 depending on what the sign of the L of u1, but the other will be non-zero. Okay. So, you have two successive cancellation decoders now. Okay. So, initially you had only a one decoder. Remember, every decoder costs you memory and storage, right. So, every decoder has a state. You have to store all those L values, the beliefs that are flowing in, and the U cap values, things that are flowing back, and the states. Okay. So, you have to store all of them, and when you make a copy of this decoder, you have to copy all that information. Up to that point, all the information that you had, you have to copy. Okay. So, that happens here. So, this is copied, this so you copy internal decoder data. Okay. So, this is very important. Okay. So, you have to copy this, and except for the last decision. Okay. So, the last decision alone is different. Right. So, except for the u1 which was decided as 0 in this SE decoder 1, in this SE decoder 2, u1 would have been decided as 1. Okay. So, you will have two different decoders, two different path metrics, but most of it will be the same. Okay. Up to that point it is the same. Okay. Only there it differs. Okay. The next you go on to u2, again I am assuming this u2 is the is not frozen. Then what do? You again divert it into 2. Okay. So, you make both decision 0 and 1, and this path metric, one more decision metric will be added. So, like I said, this is decision metric 1 of 0, this is decision metric 1 of 1. Likewise, this I will call decision metric on the first decoder for the second bit when you make a decision 0. Okay. Likewise, here decision metric in the second decoder, no, the first decoder, sorry, this is the first decoder still, for the second bit when you make a decision 1. Okay. So, this decision metric gets added to this decision metric gets added to this. Okay. Again, one of these will be 0, the other will be the absolute value of the belief that came in. Okay. So, you get added here. Okay. So, we will later on when we see an example, we will sort of explicitly sketch this. Okay. So, likewise here this is dm22, okay, I am writing m in a subscript, dm22 of 0, dm22 of 1. Okay. So, these are again decision metrics that get added to the earlier path metric to get the overall path metric. Remember, again this was copied up to the u1 point, and likewise this was also copied. These are all copies. Okay. So, you will copy the first decoder to get the second decoder will sort of be renamed as the third decoder, and you will copy it to get the fourth decoder. Okay. So, remember, these 4 path metrics have to be maintained, and 4 decoders have to be maintained to be stored. Okay. So, when I say decoders are stored, all the internal information, the L values that are flowing from the top to bottom, U cap values that are flowing from bottom to top, and the states have to be copied and retained in these 4 decoders. Okay. So, what do we do at u3? Okay. What happens in the next step? Okay. So, we kept making 2 decisions for every decision. Okay. Now, in u3 also, if you make 2 decisions, in each decoder you will have 2 paths, and that becomes 8 paths. Okay. But I want only a size of 4, I do not want 8 paths. Okay. So, what you do at that point is you prune away 4 paths. Okay. You do not go to 8 paths, you throw away the 4 least reliable paths, or the 4 paths which have the higher penalty, you throw them away. Okay. So, that you go back to the 4 one. Okay. So this is a slightly tricky thing. If you think about it, you're growing the decoder first and then you're pruning it. Okay, so you have 4 decoders here. After the U3 also, after the decision U3, eventually you will have 4 decoders, but in the intermediate part you have 8 decoders. Okay, and then you throw away 4 of them and you have only 4 decoders. Okay, so this is how the list decoder proceeds. I'm going to show that in the next slide, but hopefully this is clear, so you get a feel for how it happens. I'm not showing the internals of each of these decoders. They sort of proceed in the same way, only when they make decisions they have this kind of divergence. Okay, so this is what happens in size equals 4 decoder in general. Okay, so this is a more general picture at a particular node UI. Okay, so you have 4 decoders coming in. Okay, so before the decision on I, you have 4 decoders and 4 path metrics, PM1, PM2, PM3, PM4. Okay, there will be 4 path metrics, and then you come into UI, right, and then you make a decision. It could be 0 or 1. So again, once again, I'm assuming not frozen. Okay, if it is frozen, if the ith bit is frozen, there is no problem. Okay, the decision is always 0, 4 remains 4. Okay, so if it's frozen, I don't have to show anything more, 4 remains 4. I will only have to update the path metrics depending on the sign of L of UI. Okay, if L of UI is positive, there is no update to do, it's just same path metric. If it is negative, then you add the absolute value of L of UI to this. So if it's frozen, that's what you do. Frozen is very easy, there's nothing much to do. If it is not frozen, then you have to make both decisions on each UI. Okay, 0 and 1, 0 and 1. Okay, so you end up getting 8 different path metrics here. You throw away 4 of them. These are the high path metrics. Okay, so you sort and select the least 4. The higher 4 path metrics are thrown away and you keep only the lower 4. Okay, so now if you think carefully about it, this involves more copying and moving around of data between the decoders. Okay, so I see decoder 1 alone moves here. Okay, so this will be copied here. Okay, so what happens here? This one is copied there. This is okay. So both of these are retained in only one way. Now what happens here? This SC decoder 3 is totally deleted. It didn't survive at all. It made some other mistake. On the other hand, this is copied twice. Okay, maybe I'll show it from the same starting point so that you see where it goes. Copy 1, copy 2. Okay, so you make 2 copies so that it still maintains on the after the splitting and the pruning. Okay, so lot of other things can happen. Okay, so it may happen that such things don't happen. All the decoders survive, one from each survives, but that is a little bit unlikely. There will always be a situation where one splits into 2. All of that will happen. So all of that involves moving data between these decoders, because each of these decoders were sort of functioning with their own tree. Okay, each of them have their own tree with their own L matrices and this U cap matrices. You have to move them around to make sure that this whole thing will work. Okay, so this is the overall thing. So you continue with 4 surviving decoders all the time. So what are the decoded code words? These are the decisions made on the 4 surviving paths at the end. At the end, you will have 4 surviving paths. Whatever decisions you made on them are the U caps that you have. That you check CRC on that, and then you proceed. Okay, so this is in essence how the list decoder works. Okay, once again, I have not talked about the frozen. If UI is frozen, paths are not split. Okay, so this operation of making 2 decisions is called path splitting. Okay, so this is called path splitting. Okay, and this is pruning. Okay, so you split the path and expand it into 8 or 2 times the original list size, and then you prune it down to bring it back to M. Okay, so if UI is frozen, paths are not split, path metrics may be updated. Okay, so the updating of the path metrics will happen, but paths are not split if UI is frozen. Okay, so hopefully this is clear to you. So this is how the list decoder proceeds, and when we implement it, you'll see that there are some lots of carry to take. It's a little bit more complicated than the successive cancellation decoder, which we could implement very easily, but it's just essentially making multiple copies of that and working with them. Okay, so I think that's it. That's the end of this lecture on successive cancellation list decoding. In the next lecture, we will talk a little bit about the implementation of this, how we go about implementing it, what are the data structures, etc. And then finally, we will write some MATLAB code for this. Okay, and that more or less is the end of the course. After that, I will have some conclusions where I will look at performance and all. Okay, thank you very much.